presentation today is a modeling and a simulation of district heat pipeline system. This is an extended application of electromagnetic transient simulation. The presentation will cover this content. First, the background of the multi-energy flow. The second is the frame of EMT solution. And the third is the modeling of heating network. Then the fourth and fifth is the improvement we have developed to fit the heat network in EMT solution, which is one is the bidirectional modeling of the heating pipe, and the other is the hydraulic dynamics of the heating pipe. And the later one will, based on those models, will introduce implementation of the pipe models on real-time simulator. Then I'm going to provide some of the conclusion and the future work. So first, background of the multi-energy flow. The future, building energy supply in various forms. So because now we have like the residential of all the office building, the energy supply usually it was all electrical. Now some of the energy, especially in the European country and some part of China, people said if we can provide the heat energy and will provide some other electricity at the same time, it will overall increase the efficiency. The heating and electricity can compromise with each other, then reduce the cost overall, and also better protect the environment. So for that, we developed the CHP, also developed the heating network, also developed some of the hydrogen and the manufacturing and the fuel cell, which is a hydrogen applications in power system. This is, if you look at this, this is some of the, sorry, this one. Is it residential buildings, or is this work? I don't know if it's work or not, but. So, for example, this is the building energy supply. We used to only supply the electrical, now we can supply the then if we supply the energies through this working? Which way is working? I don't think so. Okay, that's okay. Yeah. So we will develop the electrical part, which is the power system we have been using for many years, and also we developed the CHP, so the united supply of the heating and the electrical power. For some of the power plant, we have steam turbine and the other form of energy supply. Then we can generate electricity. In the meantime, provide the heat. Then the heat energy will supply through all the pipe to the neighborhood residential or office building or the other buildings. So for that, this is a sort of a requirement from the industry or from the society. Then we have developed these models. This is today's simulation, like the presentation is introduced one of the work to. This is I myself is very interesting. Then I spoke this with Professor Xu on the PSPES general meeting. Then we decided I'm going to just introduce this simple the idea or the concept on this conference, and see if the young people can be inspired to do some similar exploration. For the EMT, we know the EMT simulations, basically, this is a very mature algorithm developed 60 years ago. Then, 60 years ago, by Professor Hermann Daumel, who recently passed away. So we had some memorial service on this PS general meeting for him specifically. So this is what he has been done is using this solve the power system in a circuit form. Basically, it solves the circuits itself. So for example, if you have three-phase power system, then normally we use a phasor. We don't solve it in the instantaneous value. Use a phasor is much simpler for the transient stability. But for EMT simulation, is include the transients in the network. So basically, the idea actually is very easy actually from the modeling part, because we don't need to develop any models. We just solve the circuit. For this, for example, this is RC circuit, RLC circuit. If for example the L, then we have V equal to L di dt. Then for that we using the numerical integration to write the equations. Then we use the trapezoidal integration format to describe the formula. Then finally, all the current at the current time step can be equal to the inductance times the voltage plus the I history, which is history current. For example, for that format, if every component has this format, then we can solve this differential equation in the form of algebraic equation. This is downsized one layer, so you can solve the dynamic using some linear equations. So basically, it's not a node analysis. If we, for example, transformer and valve group or transmission line, if we can write out all these normal equations, then we can solve it very easily using the node analysis, which we have been taught well in the second year of the university. So, in the past 60 years, the EMT technology, simulation technology, has been well developed. Now the technology is very mature on the node analysis, include the improved node analysis. Also, we can solve very large systems. For example, over 10,000 bus. Number of equations can be, for example, if you have 10,000 bus, basically at least the number of equations must be 30,000, because we have three-phase in power system, plus many dynamics in the control system. So the entire dimension is much higher than that. But now that we have solved that problem in the past 60 years, we use advanced parallel technologies at all levels, for the component level, from the network solution level, and from the entire power system level. So that's well developed. And the real-time simulation also we use lots of matrix sparsity. This has been developed by the mathematical community and used by many pioneers of power system, including Professor Daumer and other pioneers. So in the EMTP and in the other power system analysis software. So we have accumulated many experience in the past 60 years. In the recent 30 years, we developed a real-time simulation, which we can develop the simulation tools in real time, then do the hardware in loop testing using the digital simulation. This is one of the advantage. And we have to test the equipment without connected to the real power network. So the procedure of the hardware in loop simulation today is very well developed. So this is one of the things, if people want to do the other technologies, for example, the heat network, if they want to test this, if they want to develop another set of tools to do the heat network simulation, then they have to develop the first software, second the hardware, then they do the hardware test the control of the heating network. That will be very complicated. But if you directly use EMT simulation tool, which has been well developed, then we can just save a lot of times. So the question is, are there any opportunities to use these EMT technologies in other domains? This is one of the try is to do it in the modeling the heat network, which I'm going to talk about today. Well, if we look at the heating network, the critical, most important component is the pipe. Pipe is the key model. So the pipe of actually heat transfer in the pipe is kind of very special. It's called advocation. I think for the translate in the last flow, this is called 叫平流. This is a special word because the energy, actually the heat energy, is not transferred like for example, you have a metal, then you put the heat this side, then the other side will also be heated gradually. But this on the pipe is not like that. The energy is carried by some of the moving mass flow, mostly water. So just people put the water, the heated water, warm water or hot water in the pipe, then the water itself carry the energy. So this is called advocation. And so the model needs to include both sets of equations. One is hydraulic, is the water flow. The other thing is the thermal model, is the enthalpy or the heat energy, which has been is transmitted in the pipe. So this is a pretty interesting questions. So now we have two problems. So in order to do that, first we establish the hydraulic and thermal models, like the transform models, whatever other models in the simulation. The second is how we fit this non-electrical model in the solver of the electric power system, EMT solver. So it is interesting if we compare to the heating system and power system, it's kind of similar because we have the voltage, the current, and the resistor, and the capacitor, or the reactors, this on the electrical side. But if you compare the thermal side, we call it like a potential. We call voltage is also voltage potential, right? So this is a corresponding element variable is temperature, and the flow we have current, but this is the heating transfer. We have the heating transfer here. It's enthalpy, and the electrical resistance in the corresponding part is called thermal resistance. When the actually heat is transferred, it also has the resistance to try to block it. So it takes some heating drop. In other words, if you put some heat here to transfer to the other side, it must have some drop or some loss in between that. So this is modeled by the heating resistance. And also capacitors. So the interesting thing is also on the hydraulic part, we have pressure, and we have mass flow, and we have hydraulic resistance. What is hydraulic resistance? It's basically the friction, which stop you to try to move the water forward. 实际上就是摩擦，所以管道摩擦壁所引起。是它 try to 阻碍这个流体的往前前行的一种力量。So if we can actually solve this with the Newton's law in the mechanicals, based on this understanding, we can my friend Kai Chongzi and his student developed a method to try to model this in equivalent network. So this is, for example, this is one of the pipe is over there. This is a piece of pipe. Then we have the enthalpy to be transferred from this starting point called inlet and outlet. Then if we can treat the pipe in the many part, for example, the dx is a distance between the beginning of the pipe, the inlet, and the outlet, and this is a resistance, the heat resistance, which we try there's some loss to transfer to the ambient of this pipe. So 因为这个热在这个管道里流，那里面很热，外面很凉。那实际上环境很冷的话，温度如果不一样的话，它肯定有损耗，它要流出去。So we are not power thermal engineers. So I have tried to explain this some in English and in Chinese. For that, then we can develop this model. We have this is the parallel part. This part is the loss on the heating actual radiation, or is conducting to the ambient, to the outside environment. And this is the heat or the energy, which is a capacitor to store in the fluid itself, in the fluid flow itself. Then anyway, for that, this paper tells you exactly how to do that. Then the up channel is the hydraulic part. Then the hydraulic part, actually the mass flow decide the called specific heat transfer. This is HT. Then this is decided by the entropy, decided by the mass flow and the specific heat. Is called 叫比热。比热如果乘以它的流速的话，那就等于它的entropy 能量。For that, we developed this pipe model, which is 2-dimension, which is the first one. The up one is the mass flow, it's hydraulic one. The lower one is entropy transfer. It's a thermal one. So this has been developed by some of the other research in the Berlin Technical University. What we have done is try to fit this in the EMT solver. In order to do that, we have to solve two solutions. One is the bidirection of the flows support this. The other one is the water inertia. So when the water is started to flow, it's not flow right away. There must be some inertia. So we developed this improvement in the model. Then the other things, besides the pump, other stuff is pretty straightforward. So basically, we need the pump model to generate the pressure to move the water, and we have the junctions. In the junctions, we just use the KCL like a circuit, and we also have heat exchanger. This is one of the model of heat exchanger and heat load, and we have some reference point, which is just for the observation. So now how to deal with because the heating, the water is the heating is the current can be flow from this direction, also from that direction. How to solve this? Because right now the equivalent electric circuits is only one direction. So in the previous paper, so we take these equations, then the original model just be included by some of the functions we will explain here. So so we developed this improvement in order to fit this component in the EMT solver. So for this is the original model. This is the hydraulic part, and this is the thermal part. Then if we connect many pieces of it, it becomes this. Why we connect many pieces of that? Because this can be increase the precision of the accuracy of the modeling of heat network. I'm going to show you before later on. So for this is the up one is hydraulic one. It's very simple, just the variable resistance, and the thermal calculation of this model of this thermal one. We use this part of circuit, or we use this part in here in this thermal calculation. Then besides this, when we develop this technique, if the flow is from this side, right-hand side to the left-hand side, we assume we let the G3, the grounding G equal to 0, and r equal to 0, but G1 equal to 1 and r equal to Tn. Then we just solve it in the network solution, then we will get exactly the temperature solution. Then for that, then on the other direction, we can do is similar technique. By this solution, then we can do the bidirectional transfer. This is the ideal water. This water temperature. Yeah, the proposed model actually is equal to the original model, but the advantage is we can do the bidirectional. And we also check the impact of the number of segments for the pipe. Then we can see that if the number of segments increase, then the accuracy will be increased. To some point, then it will be saturated. We can test this, then we can decide how many segments we need to do. This is like a transmission line. If we use pi section to model transmission line, if we increase the number of pi sections, then to some point, it will be equal to the traveling wave transmission line. We can decide, we can try and error and then to decide. Then the other thing we add in the hydraulic dynamics is we add it was a model in the previous work modeled by resistor of the hydraulic resistor. Then we add a reactance inductor in it, in the circuit. This inductor can be defined, can be calculated by the speed of water transfer, water movement. Then into this, because we know if we try pressure on the water, it will not, the speed will not up to the constant speed. They will gradually to increase. This is, everyone knows, this is inertia. So by this point, basically we include the dynamics of the water flow, the hydraulic dynamics. Then to do this, then increase this, then we can see if we don't have the mass flow, then the speed will look like this. The water move is the mass flow rate will be immediately increased. However, if we increase this with the inductor in this, is much smaller, much closer to the reality in the physical as a physical phenomenon. However, if this is a time step is pretty bigger. If we want to bypass this the inertia to start it faster, then we can use some of the special method. That is when it's started, when we started the model, we can start it without the inductor. Then if we go to once the model is started, then we can put insert the inductor in. Then once we change, we can see the dynamics. This is the initialization of the fast initialization, which we bypass this inductor, also bypass the inertia, so that we can bypass the inertia. Then this is the modeling. In order to implement the real-time simulator, we have to, because we have this the heat pipeline, but the heat and the power system model, they are different in the time constant. So one of the electrical part circuit is very faster, but the hydraulic is very slow. So we cannot solve it. We shouldn't solve it in the same time step. For that, we developed the multi-ready simulation hierarchy box in RTDS. Then in that, we can define the time step of this heating flow to 1 second. Then while the power system part is still 50 microseconds or even less. Then finally, we can integrate the entire network into one. Basically, this is the conclusion. This speech introduces a method for modeling and simulating the district heating pipeline system within the framework of EMT simulation. We solved two technical problems. One is how to achieve bidirectional propagation of the thermal energy in the pipelines. The second is how to simulate the dynamics process of the thermal energy propagation within the pipeline. So it's a hydraulic pipe, the dynamics are included. So this work is just an attempt to extend the application of the EMT solver, which we can do. Right now we can do the closed loop simulation. So hope the audience, if you are interested to do this, if you have a system which is like a transmission line or is some distance or the advocation phenomena which you want to solve it, but you don't want to develop the entire solver or the testing facility, then you can directly use the RTDS or other EMT simulation tool to solve that without significant effort. I think that's what I want to introduce today. Thank you.
Thank you, Dr. Zhang. Dr. Zhang is a long-time peer friend of the Purple Mountain Forum. So I will sincerely thank him for his continued support. Thank you very much. Now let's move on to the question and answer part. Since Dr. Zhang is comfortable in Chinese and English, so you can feel free to ask a question in either language. So, any question? This gentleman, please.
Thank you, Dr. Zhang. I'm Wang Guoning from State Grid Electric Power Research Institute. Thanks for your sharing on modeling and simulation of heating pipeline. I'd like to ask for bidirectional pipe simulation. How do you model the dynamic behavior when flow direction changes?
Okay, thanks. I think if you have the inertia in it, then if you want to change the direction of the flow, then you cannot change it in a sudden. You have to reduce to zero, then back again. Then include the speed, the mass rate will be decreased to zero. Then you ramp it again in other direction. So that is how if we reduce if we increase if we for example in the circuit, then we flip the voltage, then the current will not change right away. It will first go to zero, then go back if it's a direct circuit. I don't know if I answer your question.
Okay, thank you.
Yeah. Thank you. So let's go to the last question. This gentleman, please.